welcome to the second of the Hot Materials seminars, and I'm very excited to introduce Professor Gennady Shvets. So just to give you a very quick background, Professor Shvets comes to us most recently from UT Austin, where now he's a faculty member here at Cornell, but he's had a kind of interesting background, and I think that'll come across in his presentation. He actually started out as a plasma physicist, and now he, of course, he's still doing plasma physics, but he does both theory and experimental work in plasmonics and metamaterial, which could be thought of, for instance, as a branch of materials, but also could be thought of as a branch of optics. So that's what he's going to tell us about today. So, Professor.
Okay, thank you for inviting me. Yeah, I'm the audience, and you can see that we're taking safety serious thing here. Okay, so I'm going to be talking about a very special kind of materials. These are man-made metamaterials, and you know, just to explain the word, because this may be a word that you have not encountered before, we call it a meta because of the Greek word meta, which means going beyond. So metamaterials are basically trying to take us to new sorts of materials that are not readily available in nature. So this is something that you cannot just dig out of from the ground. This is something that you need to artificially synthesize. And I mean, you probably heard about meta before, maybe in some negative context. For example, metaphysics, that would be trying to go beyond physics. So with our materials, we're not trying to go beyond nature or to go beyond anything that's possible within the laws of physics, but we're trying to go beyond something that's readily available. And these are just some of the examples of the structures that are popular, that have been used and that are popular in the metamaterials area. So you can see that the ingredients, the actual materials, can be quite conventional, would be just metal, or this slightly unconventional. I will be talking a little bit about integrating two-dimensional materials, such as graphene, for example, with metallic structures. But overall, the ingredients are pretty common. What is uncommon is how you combine them together in order to get some interesting functionalities that are not available from conventional materials. So actually, the field of metamaterials is very broad, and you may have heard some talks about mechanical metamaterials. So you can make materials that have very strange, for example, modules or other properties. So metamaterials is very, very broad. But since my work is mostly in the field of optics and electromagnetics, so the type of materials that I will be talking about are electromagnetic materials. So they have unusual optical and electromagnetic materials, but other properties will be quite conventional. Okay, so I'll give you a little bit of history because this is now a relatively mature field by standards of new fields. And of course, some fields of physics extends to new them. So it's a pretty young standard. But well, actually, a little bit, right? So back. But this field is about 15 years old, and some of the initial work in this area came from the realization that you can artificially make materials that have dielectric permittivity and magnetic permeability simultaneously. If you've taken your freshman electrodynamics, you already know what these numbers mean, epsilon and mu. So, for example, if you have a piece of glass, it has a dielectric constant of about 2.25, and if you take a piece of silicon, epsilon would be 12.25. But these are all positive numbers, right? So, people that really interested in the prospect of making both the epsilon, which is dielectric permittivity, and mu, magnetic permeability, simultaneously negative. So why did they get so excited about it? Because they realized that if you calculate the refractive index in a material like that, you will get, you will have to take the square root of a product of two negative numbers, and you can choose positive sign or negative sign. Most of the time we choose positive sign when we're dealing with materials that have both positive epsilon and mu, but it turns out that when they're both negative, you actually have to take a negative sign. And this has a very interesting implication. So, when you take a square root of this, you get a negative sign. As I'm going to show, sorry, you are going to get, for example, effects such as abnormal refraction. We are going to get some other very interesting electromagnetic phenomena, and such materials definitely cannot be obtained in nature. In other words, if you try to order a lens with a negative refractive index, you can go through various catalogs, you can just give it a try, but you're not going to succeed. So this is something that really has to be synthesized. So let me show you a couple of movies, a couple of examples that show how negative refractive index can be very different from positive refractive index. So let me play this first movie. So this will show an example of electromagnetic waves propagating in a medium that have both positive epsilon and mu, okay? So let's see. So you see that the pulse is moving from left to right. Oops, I interrupted it too early. So the pulse is moving from left to right, and the cycles are also running in the same direction. So now let's do exactly the same animation, but we're going to use a negative index medium that has negative epsilon and negative mu. Okay, so let's see what's going to happen. Okay, so you see the difference? Still moving from left to right, but now all the cycles are running in the opposite direction. So this is very strange, very unusual. It actually gets curiouser and curiouser, as you are going to see, okay? So let's imagine that you have a pulse coming in from a regular medium, okay, epsilon positive, mu positive, into a negative index medium. So the pulse keeps going in the same direction, but now the cycles are running in the opposite direction. So what is really interesting about this media is that the group velocity and the phase velocity are pointing in opposite directions, right? Because the direction in which the cycles are moving, that's your phase velocity. The direction in which your energy is moving or your pulse is moving, that's your group velocity. And previously it has been assumed that those always have to be in the same direction, but it turns out that this is not the case. So this actually has very interesting implications for refraction. So far I only showed you what happens when you hit, for example, an interface normally. What if you hit some interface at an angle? So this is really interesting. So for example, if you have a slab of regular material, this is how light gets refracted, right? So you can actually get sort of a pseudo image. You cannot get a direct image. On the other hand, if you have a slab of negative index material, you will see that the rays are hitting it, for example, at this angle. And then when they refract, the rays actually end up on the same side of the normal to this interface. So you can actually get even two foci, one inside the medium and another one outside. And this device, which is a very interesting device, it's a flat slab of material, it can actually act as a lens. So it became known as a Bisilago lens after a person who first phenomenologically proposed this kind of a negative index material. He didn't know how to make it. He just said, well, if we can somehow come up with something like that, this is what's going to happen. Okay, so let me show you another example of what sorts of fun things can happen when you have a glass of negative index water and you put a straw in it. You can see that actually the straw looks like it's pointing in the wrong direction. So nobody has ever made a glass of negative index water. It is still very, very challenging, and it will definitely involve plasmonic nanoparticles. So, you know, if somebody offers you you know, a glass of negative index water, if you really think that it's negative index water, don't drink it, okay? Because it will have lots of various nanoparticles, which may or may not be safe. Okay, let me show you another kind of an animation of what happens when we take a ball and we drop it into a pool of negative index fluid, okay? So if you drop it into a regular pool, right, what you are going to see is that as the ball moves away from you, it will get smaller and smaller and smaller. So you see, it's just going, it's sinking, right? It's going to the bottom of the pool, okay? Let's see what happens with a negative index pool. Okay, it starts getting smaller. Well, but look at this. Okay, now it's going to look like it's expanding. So this will be a little homework for you. So when you go home tonight, maybe try to work it out. Why is it that the ball, which is moving away from you in the negative index water, why does it look like it's expanding? So it's kind of simple optics, but you'll enjoy it. Okay, so people were obviously motivated by all these interesting possibilities, so they started thinking about how to make such materials, and several designs were proposed. Most of them actually used very simple ingredients, and these ingredients could be metallic rods, for example, or little resonators that are sometimes called split ring resonators. I'll tell you a little bit later about why this is such an interesting ingredient. And people had a lot of fun with it. So from the split rings, they managed to get a negative mu. From these metal posts, they got negative epsilon. So they actually demonstrated negative refraction and things like that. Now, I must say that this particular line of pursuit, getting negative refraction, did not turn out to be extremely promising, even though it's a lot of fun to think about, but it turned out that, the applications were not exactly there. However, people have learned quite a few things about these metamaterials. For example, they learned some of the basic ingredients, such as, for example, the split rings and metallic rods and things like that. They figured out that these materials will almost certainly be resonant, okay? So you cannot really have negative epsilon and mu for all frequencies. There will be certain ranges of frequencies for which you can get negative values. And when you hit these resonances, you can actually get very significant concentration of energy inside metamaterials. And actually, this is something that captivated, especially those who are interested in applications, most of all. That these materials can actually strongly concentrate energy, and then you can use this concentration to various ends to advance different applications. Okay. So now another thing that became clear as people started studying metamaterials is that they represent a very interesting state of matter, which is a little bit different from regular materials. So regular materials consist of atoms, and atoms, of course, an atom is extremely small, right? The size of an atom is an angstrom. And when you start looking at how atoms interact with electromagnetic waves, you have something tiny interacting with a wave that has a very long wavelength, right? So, for example, for visible light, that the wavelength is going to be between 500 and 700 nanometers, right? So you divide this by an angstrom and you get more than 3 orders of magnitude, right? So it turns out that this is actually a very significant limitations on the properties that these materials, natural materials, can have. Okay, so for example, one of the limitations is that natural materials cannot have negative mu. They cannot have negative magnetic permeabilities for optical frequencies, and that's a serious limitation. It actually prevents us from making negative index materials. Now, there is another end of the spectrum, and maybe some of you have heard about it. Maybe you've heard about photonic crystals. So photonic crystals are also similar to metamaterials in a sense that they're built out of conventional materials, but those materials are arranged in a periodic way in such a way that basically the spacing between them is approximately wavelengths divided by 2 or so. Okay, so such structures can also have lots of interesting applications and very interesting properties. But for example, we cannot what people call homogenize these materials. So what does it mean, homogenize? We cannot introduce averaged quantities like an average dielectric permittivity or average magnetic permeability, because the unit cell that you are averaging over is actually comparable to the wavelengths of light. So there's no point in averaging. So metamaterials are actually kind of in between. So they're much bigger than an atom, obviously, but at the same time, they're much smaller than the wavelengths of light. So they sort of get the best of the two worlds. On one hand, you can homogenize them because the unit cell is still much smaller than the wavelengths of radiation that's propagating through them. So that's a good thing. It's they're a little bit easier to understand. At the same time, they can have some of the properties that are not allowed in normal materials. For example, you can have what is called optical magnetism, which means magnetic response to optical frequencies. So this is something that was understood from the earlier days of metamaterials. Now, since then, of course, the field exploded. And even though initially people were thinking about three-dimensional materials, they very quickly realized that, well, you don't really need to go all the way to 3 dimensions, right? You can even make metamolecules, and various techniques are available for making such artificial molecules. For example, people use strands of DNA to combine plasmonic structures into clusters. People use atomic force manipulation to assemble them into tiny nanostructures. So you can make all sorts of artificial molecules. You can also lay them out in 2-dimensional patterns. So a conventional metamaterial would be 3-dimensional. Here, everything is just laid out on a surface. And it turns out that these are also very useful objects because they allow you to make extremely thin lenses, various polarizers, devices that can, for example, convert linearly polarized light into circularly polarized light, or emit thermal radiation, which is, for example, circularly polarized, which is very strange because normally thermal emission is completely unpolarized. So there are all sorts of interesting things that we can do in 2D. And in fact, I will show you some movies and some examples of how one can use these 2-dimensional metamaterials to study biological objects. So some people here are from the chemistry REU, right? At least that's what I heard. Okay, so this will be of some interest. And of course, if you want, you can go all the way and make full 3-dimensional metamaterials. Okay, so here's what I'll be talking about. I just selected a couple of topics that I think are appropriate for a lunch seminar. Okay, not super tasking, but interesting. So I already gave you this brief introduction to metamaterials. So I will tell you about how we integrate natural 2-dimensional materials, such as graphene, for example, with metamaterials and metasurfaces. And this allows us to make various devices that can respond on a very rapid time scale. So for example, you can make a lens that has a focal length that is changing as a function of time, that is rapidly changing, things like that. I will also show you how metamaterials and metasurfaces are even helping us now to search for cancer cells and even to develop new drugs and new cocktails that could be more effective than before. Okay, so first of all, just to lay out a little bit of framework and to explain how a metamaterial or a metasurface works, let's just look at a very simple element of a metasurface. So this is a split ring, okay? So this is how it looks like. So imagine that you have some currents flowing in this ring, for example, like this. So this current is going to induce magnetic field, right? So magnetic field is going to produce some flux, okay? So if current produces flux, it means that this element has a certain inductance, right? because as you recall, right, flux is inductance times current. At the same time, because of this break, right, there's going to be some charges accumulating on the two sides of the ring. And that means that there's going to be a certain capacitance to this element. So one can actually start thinking about it in more engineering terms and think of a metasurface as an LC circuit, right? So if you have an LC circuit, there is a natural frequency of an LC circuit, right? And if you want to somehow play around with this frequency, somehow change it, tune it, then you will basically have to change one of these numbers, right? You will have to change the inductance, or you will have to change the capacitance for both. So, if you have a capacitor and you want to change its capacitance, what are your options? What would you do? What?
Surface area.
You could change the surface area, but let's say you're allowed to add something or remove something or put something inside. What would you do? Exactly. You could drop a piece of the electric. In fact, you could, if you want, you can even drop a piece of metal inside your capacitor, and you're going to change the capacitance. Now, changing the inductance is a little bit trickier, okay? But it turns out people figured out how to do this. So if you want to change the inductance, you may want to place some sort of a highly conducting sheet very close to your LC circuit. So why? Because if currents start flowing around the circuit, right, they're going to produce certain magnetic field. They're going to produce certain flux through this conducting surface, right? And by Faraday's law, the surface is not going to like that, right? It will produce its own countercurrent, right? And this countercurrent will diminish the flux that's passing through your unit cell. So this way you can change the inductance of your circuit. So you can start basically playing around with C and L, and hopefully you can even do it in real time. If you can find some materials that respond very quickly. In other words, it's unlikely that you'll be able to very quickly on a nanosecond scale start dropping something into a nanoscale structure, right? This will be very hard. But it turns out that there are certain materials, and one of these materials is graphene, which is extremely thin, and it also responds very rapidly to external electric fields that you can actually use as this sort of a highly conducting sheet, right? So just to tell you a little bit about graphene and how it's usually utilized in these sorts of structures. Graphene is placed on top of an insulator. So in this particular case, an insulator is silicon oxide, and gate voltage is applied between, for example, a semiconductor such as silicon and graphene, right? So basically, every field line has to start on graphene or terminate on graphene, and that basically connects the voltage that you are applying across this insulator with a charge carrier density inside graphene. So in this particular case, when we're applying this kind of a voltage, you are injecting holes into graphene. If I flip the voltage, then of course I will start injecting electrons into graphene, right? And if I can do it very quickly, then I can vary the density of carriers very rapidly. Now, why is it important to change the density of carriers? Because the more carriers you have, the higher is the conductance, right? So, and in fact, there is a very simple formula that connects the conductance to the so-called Fermi energy. So Fermi energy, as you recall, electrons and holes obey the Dirac statistics, right? So if you have a certain density of carriers, they're going to fill up the band zone all the way up to a certain Fermi level. So these two quantities are basically interchangeable, the density of carriers and the Fermi energy. Okay, so then as you're injecting these carriers and increasing the conductance of your sheet, you can actually move the frequency of the resonance of your circuit, And in fact, what you are going to do is you are going to reduce the inductance. And remember, the frequency is 1 over square root over the inductance. So that means that you are increasing its eigenfrequency, or you're shifting the response of your metasurface, which could be reflection or transmission or absorption. It doesn't really matter. You can measure whatever you want, but this optical response is going to be shifted onto the blue side because the frequency goes up. So that means that the wavelengths of resonance goes down, and you're shifting from red to blue. Okay. So now it turns out that matching up these sorts of two-dimensional materials and metamaterials is really a very nice, a perfect match. Okay. So why is it a perfect match? So I already told you that integrating these two-dimensional materials with metamaterials is good because you can very quickly change their properties. So that means that you can change the property of the material overall. Okay, so that's what two-dimensional materials are doing for metasurfaces. What can metasurfaces do for the two-dimensional materials? Well, two-dimensional materials do not respond very strongly to light. Okay, so graphene, for example, gives about 2.3% drop in transmission when you pass light, through graphene, and that's the reason you can actually see graphene with your bare eyes. Okay, so this is a remarkable number, right? 2.3% for something which is 1 atom thick. Okay, so this was a really amazing finding that you can even get 2.3%. But of course, if you are thinking about something geared towards applications, you probably do not want to change your transmission or reflection just by 2.3%. Maybe you want to go by, 10 decibels, right? Maybe you want to change it by an order of magnitude. And obviously, two-dimensional materials by themselves cannot do that because they're just too thin, too small. On the other hand, if you integrate them with plasmonic or metallic metasurfaces, those metasurfaces can concentrate light intensity to an enormous degree. So this is an example of a split ring which has a tiny gap. So this gap is only 70 nanometers. And you can see that the intensity of light in this gap goes up by a factor of 6,000. Okay, so you might say, oh, but this isn't a tiny gap. So if you integrate over the area, it's not going to give you much, right? But even if you integrate over the area, you're still going to get a factor of more than 30, right? So now you multiply 2.3% by 30, and we're talking real numbers, right? So, so that's basically showing how metamaterials and two-dimensional materials are really working, to enhance each other. Okay, so what can one make from these sorts of integrated materials? So one simple device that one can make is the so-called modulator. So a modulator takes a stream of photons, for example, and breaks them up into reflected and non-reflected photons. So you can actually encode some information into your optical stream by creating a string of zeros and ones by simply applying some gate voltage to your device and modulating the reflectivity or transmission of a structure like this. So this is done basically by applying voltage and shifting the resonant wavelengths of your structure by quite a bit. So you can see here as you're injecting holes, from nothing to about 5 × 10⁻¹² per square centimeter, which is a fairly high areal concentration of carriers, you're changing your frequency from 7.4 to about 7 microns. So this is already a significant change, and this change has important implications. So as you're changing the resonance from here to there, you can see that the response curve, which in this case is reflectivity, but it could be anything, is changing by a lot. So you start by reflecting 20% of light, apply voltage, and now you're suddenly down to 2%. So you've modulated the reflectivity of your signal by a factor of 10, and you can do it extremely fast. You can do it as it turns out, on a scale of just a few nanoseconds. So this is very fast. Okay, now let me move on to a slightly different type of an application. So this is the work that we're doing in our lab on looking at how metamaterials and metasurfaces can be used for biological detection of cancerous conditions in a cell, and basically understanding what is happening with a cell. So why does it even make any sense to integrate metamaterials with live matter? Okay, so just to go back by one slide. So if you look at this scale of wavelengths that we're working with, you will recognize that this spectral range is sometimes referred to as mid-infrared. Okay, so what is mid-infrared? You know, visible, right? So this is a little bit less than a micron. Then you move up in wavelengths, you get up to telecommunication frequencies, about 1.5 microns. So this is the light that you cannot see with your eyes, right? So this is infrared or near infrared light. And then you can start pushing even further towards the thermal emission wavelength. So for example, our bodies emit at about 10 microns. This is, how this is the spectrum that night vision cameras capture and so on. So this frequency range is referred to as the mid-infrared part of the spectrum. Why is it so special? It's special because lots of large molecules, lots of biological molecules have resonances at that part of the spectrum. So when you look at various vibrational modes or torsional modes of various molecules, this is where their resonances lie. So in principle, being able to enhance the signal at those frequencies can reveal something about the composition of a cell, for example, or a particular region of a cell. Okay, so this is just an example of a spectrum of a cellular membrane, and you can see, so this is the absorbance. When you send the light through the cell, you get this kind of a fence of lines, but each of these lines actually corresponds to various vibrational modes, and by looking at the relative strengths of these modes, you can figure out which proteins or which groups are represented in the material that you're sensing. Okay, so what would be really nice is if we could find some way of differentiating between different types of cells, if we could figure out where those cells are coming from, telling whether these cells are normal or they're neoplastic, and it would be also nice if we could somehow subject them to certain drugs, for example, and see what is the effect of the drug on the cell. Okay, so just to kind of repeat the objective, let's imagine that somebody, a surgeon is doing surgery, and he or she would like to know where the boundary between normal tissue and cancerous tissue lies, right? So it's actually a very important question, because the surgeon needs to know what to cut, right? How deep he needs to cut. And it would be really nice if there was some sort of a simple optical technique that would reveal this kind of an information. Another very interesting application is looking at the so-called circulating tumor cells. So these are cells that come from an already developed cancer, or already developed tumor. So the tumor starts shedding cells into the bloodstream, and then those cells can go anywhere. They can enter other organs, metastasize, and then go back into the bloodstream, right? So what would be really nice is to be able to, without doing any surgery, just draw some blood, look at the spectra of the cells, count them, figure out how many are already present in the bloodstream, from which organs they came, and basically do the diagnosis this way, without cutting up a patient, simply by doing what is sometimes called liquid biopsy. Okay, so so how can we do this? Well, our approach is to use metamaterials and metasurfaces that operate in the vibrational fingerprinting region of the spectrum, which is the mid-infrared. Okay, so Now, what is really interesting is not to look at the properties of the entire cell, because a cell is very complex. It has lots of organelles inside, and those organelles are more or less the same in most of the cells. However, there is a very special region of the cell, the so-called cellular membrane. So the membrane is how a cell communicates with other cells, how it decides whether it's going to attach to something, how it decides whether it is going to keep some of the injected drugs in or spit them out. So this is basically kind of like almost like a command center, okay? And the distinctions between different types of cells, for example, between normal cells and cancerous cells, are often expressed in this very tiny region of the cell, which is only 10 nanometers thick. So it's very tiny. The cell itself, your typical animal cell, is about 10 microns in radius, and you know, if it's in suspension, then it's just a sphere. If it's laid out, it's going to be flattened like a pancake, but it will still have a very large thickness, about a micron. But the membrane is tiny. It's 1/100th of the micron, right? It's only 10 nanometers, and that's of course a problem, because if you just use a lens and try to just zoom in on a 10 nanometers depth of focus, right? It's not going to work, right? Diffraction is going to limit that. Fortunately, metamaterials and metasurfaces can concentrate light in a very tiny volume, which could be comparable to the size of the cellular membrane. And that's a good thing, because then you can concentrate on something that you really care about and not on the rest of the cell, which could produce lots of noise, basically. Okay, so this is the platform that we're using. So it's a metasurface that consists of many, of an array of these sorts of specially designed split rings or bent antennas. And the nice thing about these metasurfaces is that they confine light in a very close proximity of their surface. So within 50 to 100 nanometers, which still is not 10 nanometers, but it's a lot better than, for example, a micron or so. So you get a lot of spatial confinement from a metasurface, and on top of that, you get strong concentration of light in the near field, which could be, more than an order of magnitude. So this is a nice thing, and you can, for example, deposit cells on top of a metasurface and look at their vibrational response. So what you see here is this red line. You see many very well expressed vibrational modes with a metasurface. On the other hand, if you just put your cells on a glass slide, you will see this black line, which is essentially noise, okay? So the question is, can we somehow utilize the strong signal in order to, for example, differentiate between different types of cells and tell a cancerous cell from a non-cancerous cell? And it turns out that we actually can do that. Now, it's a kind of a lengthy process before you put the cells on. You need to functionalize your metasurface. You need to put some antibodies that will bind to the cell. Then you need to attach the cells to the antibodies, and then you have to send infrared light, have it be reflected from the cells, and analyze the spectrum. And if possible, you would like to do this very fast. You don't want to wait for a cell to just drop on top of your metasurface. You would like to find some way to rapidly attract it. And it turns out that you can do this with metasurfaces as well. I already told you that you can bias, for example, a sheet of graphene electrically and change the properties of a metasurface. Likewise, you can electrically bias a metasurface itself and rapidly attract the cell to it. Okay, so this is how it's done. So we add a solution of antibodies, wait for them to get attached, and when antibodies get attached, there is a tiny difference in the reflection spectrum. It's not huge, but it's definitely detectable. Now, if we divide one by the other, we can actually get a spectral response of this layer of antibodies. These antibodies are very small. It's just a one layer of molecules. So it can be between 3 to 7 nanometers thick. It's very, very small. However, we can very clearly see all their spectral signatures. Now, the next step is to put the cells on. And this is basically done by injecting a solution of cells into the structure and waiting for this, in this particular case, waiting for the cells to attach to metasurfaces. And when they do attach, we can compare the spectral response of normal cells to the response of the cancerous cells. And in fact, you can see that there is a significant difference. We can actually see the difference between normal cells and cancerous ones. Now, what if we want to do it really, really fast? So if you want to do it fast, you have to do it using a force or a phenomenon, which is called dielectrophoresis. So what is a dielectrophoresis? Well, is anybody here working in an atom trapping lab? No? Okay, so you know that atoms could be attracted to high intensity regions of light, low intensity regions of light. Now, it turns out that with cells, you can do something very similar. You can, depending on the applied electric field, and just as a laser field is an AC field, we're applying high frequency electromagnetic waves, frequencies of hundreds of kilohertz up to a megahertz. Depending on the frequency and depending on the type of a cell, cells can be pushed away from your electrode or pushed onto the electrode. So this is an example. You're going to see how a cell is sort of lingering. Now it's going to start shaking a little bit because we're applying voltage and it gets snapped onto the metasurface. So this all happened in a matter of seconds, right? We didn't really have to wait for the gravity to do the work for us. The electrophoresis took care of it and attracted the cells. Now, we didn't really zap the cell, we didn't kill the cell. In some experiments that didn't go quite well, you can see that we actually did some damage to the cell, but not in this particular case. So you can use low enough amplitudes of the electric field to attract the cell without doing any damage to it. And what's even more interesting, it turns out that some of the cells at a given frequency will be attracted to the metasurface and some will be pushed away. And this is really interesting because now you can actually find the right frequency that will attract, for example, cancerous cells, but repel, for example, blood cells from your sensor, from your metasurface. So that's an additional way of differentiating between different cells. And now, of course, in biology, nothing is the same or repeatable, so one always needs to do statistical analysis. But we can clearly see, as a result of this kind of an analysis, that we can differentiate between different types of cells. For example, normal cells, cancer cells are sitting in this corner, normal cells are sitting in that corner. So one can clearly do the differentiation. Now, another, why did I have this extra figure? Okay, that's probably a backup. Okay, now another question that we can ask is, can we use metasurfaces to look at the effects of various drugs on cancer cells? So you probably know that at some point, chemo drugs stop working and they stop doing damage to cancer cells. Why does it happen? So there are lots of opinions and lots of theories about this, but one of the theories is that there are certain transmembrane proteins. So these are the so-called permeability glycoproteins that reach across the membrane that can grab these small drug molecules and kick them out of the cell. Okay, so if these proteins are not present, everything is great. Drugs go into the cell, stay in the cell, do its business, do their business, right? If these proteins are present and somehow are not turned off, then the drug may stop working because the proteins will start kicking them out. The good thing for us, obviously for researchers, is that these proteins are concentrated in the membrane, and therefore, if we can somehow interrogate cellular membrane, we can find out which of the additional drugs could modify these proteins, maybe cause them not to express at all or get strongly modified, and which are not. And this is an example of a very interesting experiment. And you know, at Cornell, the great thing about this place is that there are lots of colleges that are doing very different things, but frequently they come together and collaborate. So this is a collaboration with a vet school. You know, we have one of the greatest vet schools here. And so our collaborator actually is a cat, is a vet oncologist. Yeah, I don't think it's there is a specialty cat oncology. It's a veterinary oncologist. So she was able to get us some cells of untreated cat sarcoma that were treated by different combinations of drugs. So one of the drugs is a standard chemo treatment. It's a so-called doxorubicin. And it can kill some of the cells. So when you treat the cells for a certain amount of time, you know, you can kill about 70% of them. Why only 70%? Well, the problem is that this sort of resistance to chemotherapy arises, and some of the cells simply do not die for some reason. So probably the drug gets effluxed or kicked out of the cell. Okay, so people have come up with a very interesting approach. Well, why not mix this drug with something else? Why not mix it, for example, with an antibiotic? Because antibiotics actually are known to block some of these membrane proteins. Now, an antibiotic itself will not kill the cell, but if you combine it with a chemo drug, you will kill many more cells than without the antibiotic. So our question was, well, can we see that the antibiotic is doing something to the cellular membrane? So, you know, if you look at the survivability after antibiotic alone, it doesn't really kill the cell. So, you know, just by looking at what the antibiotic does in terms of survivability, you know, you may say that it does nothing. However, if you deposit these cells on a metasurface and do the infrared vibrational spectroscopy, you will find that these cells that were treated just by the antibiotic are now very distinct from the cells that were not treated by anything. So what this means is that most likely the antibiotic had some significant effect on the cellular membrane. And even though the cell, you know, doesn't know, I mean, it's alive, there's no problem with the cell, we know that this drug had some effect on the cell and is likely to make the chemo drug more effective. So these are just some of the examples of the things that one can do with metasurfaces. But one doesn't have to fabricate these metamaterials and metasurfaces on a planar substrate. For example, one can fabricate them on the tip of a fiber and then use this fiber, for example, to insert it into a patient during a surgery and so on and so forth. So one can develop a whole metamaterials laboratory on the tip of a fiber. And now this is becoming possible. You know, you probably already had a tour of CNF. So this is one of the best nanofabrication facilities in the world. And this is why, you know, people, researchers like, you know, like us and like many other people are able to make these very small but sort of very promising structures using nanofabrication techniques. Okay, I think it's probably time to wrap up. So, well, of course, all of this work that I was discussing was not done by me, right? It was done by the students, and I would like to acknowledge them. And, well, thank you for coming to this talk.
Okay, there must be lots of questions.
Let's make sure that people at Norfolk also can ask questions. Can you hear us?
I don't know how to do that.
Yeah, I'm not sure. I mean, I think I can see them, but, oh, yeah.
Yes, you can read
I'm not sure how they're gonna do it. I can see them, but I cannot hear anything that they're saying.
There's
Okay,
some-
let's
yeah.
start here.
What sort of instrumentation can you take
What instrumentation to take the spectra? So this spectra we're taking using the so-called Fourier transform infrared spectrometer. So it's basically an interferometer that has a moving mirror, and as this mirror moves, you look at the interference signal, and it allows you to get infrared spectra with very small, very fine resolution of 1 to 1,000, something like that. You asked about solution.
and then you have ATRs, ATR.
So we did not need an ATR. So let me just show you how the device looks like. Yeah, so the device looks essentially like this. So as cells are set on the metasurface, we simply illuminate the metasurface through an IR transparent substrate. So this is calcium fluoride. It's just a piece of glass which is transparent to infrared light. ATR is another great tool to get some localization, but the localization that you get from ATR is not as great as from a metasurface. So you can get maybe 300-400 nanometers localization, but here we can get down to 15.
Okay. More questions?
You sort of thought of differentiation cancer versus non-cancer. So what is running which population?
Oh, the company told us, the one that sold us the cells, they told us. Yeah.
Exactly, you differentiate. How do you tell which one represents cancer?
Well, first we did the measurements on the cancerous cell line, right? And then on the non-cancerous. So we knew ahead of time which is which. So the only thing that we had to do is to see that statistically they fall into different quadrants. But we knew ahead of time which one is cancerous and which one is not.
So you had a first sample of health.
Right, yeah, yeah.
Patient diagnosis, you have some sample that had some cancer cells.
Exactly, and when you do, when you calculate the spectra and do the statistical analysis, you will still see that they're separated, right? So then what you will need to do is to kind of train your system using well-known cell lines so that you will know which cluster is cancer, which one is non-cancer. So you can think of this as sort of a training step. And then of course there is the actual measurement.
Insurance solution in your spectrum could not be able to tell more discrete biochemical differences between cells and
Well, that we don't know yet. So ideally, we would like to be able to tell which cancer is there, right? Is it a colon cancer? Is it lung cancer? So we do not know yet if that's possible.
Okay. Did we end up having any questions from Norfolk?
Norfolk, this is your last chance.
Does anyone have a question?
Do you hear us?
They're saying something,
Oh
but
yeah, there's a little bit of volume. Can you just turn the volume?
oh, maybe that's the problem. Okay, speak up, please.
Can you hear us?
I can hear, but not.
But you can repeat.
Yeah. I will repeat your question. Yeah.
Are there any?
Yes.
Yes, please go ahead.
Okay, she's walking up.
They're walking up. So it's a student is coming up to the
Oh.
laptop.
Yes. Hi.
So your method is to detect cancer cells in the blood, or is it also done in like other fluids?
Is it in what?
Are you detecting cancer cells in the blood?
Okay. So the question was if we're detecting cancer cells in the blood. So these are not cancer cells in the blood. They're actually transferred into a medium and then transferred to PBS, which is just a solution. So we have most likely this technique will require some enrichment of cells and may or may not work with completely unfiltered blood. So some filtering will most likely have to take place.
Right, because I know that in flow cytometry, they already have the capabilities of, at least with blood cancers, to just like go through the blood and detect whether there are cancer cells there. So what is like the advantage of your method over?
So one of the advantages is that so the techniques that you are talking about are all involve some sort of tagging or staining. So they would basically involve fluorescent antibodies. So in this particular case, this is a completely label-free technique. So we do not need any tags. And, to put a tag, you already need to know that there is a certain antigen or certain receptor which is expressed on the surface of the cell. So our approach doesn't really require that.
Sure. And one more thing, sorry. So do you think you could possibly in the future utilize a neural network to maybe train your system to automatically recognize cancer cells and categorize them?
So the question, let me repeat your question. So the question is, can one use neural networks, for example, to train the system so that, this can be done in a computerized way? That is the hope, that all this analysis will not require any eyeballing, right? I mean, I showed a couple of spectra and they look different, but that's the eyeballing method, right? So eventually this will all be computerized in a sense that statistical analysis will be done on the computer, and then the computer will basically identify which cluster is what and so on.
Right. Thank you.
Thanks.
Okay, I think it's time to finish up, so let's thank Professor Shvets once again.